Welcome to breadboarding. In this video, number 15, what I'm going to be doing is updating the monitor that we disassembled back in video 12, and we're going to extend the save and load functions in those. Rather than being designed to work with the cassette tape interface, we're going to change those so they can work with the serial port that we tested in the last video. And then we're going to be using the Motorola S19 or SREC text format, which allows you to transfer binary data between computers, PCs, and smaller devices, or also use it for burning EPROMs, for example. So the SREC format, there is an article on it on Wikipedia. It's actually a lot simpler than it looks on the left-hand side of here. We're only going to be using two record types. It's a text record format. It always starts with a record with an S, and the S1 and S9 record types, the only ones we're going to be using. So the S1 record type is for 16-bit addresses, and there are other record types for 24-bit addresses, 32-bit addresses. So we're only going to be using these. The format's fairly simple. It includes a count of the number of bytes. So this is not just the data byte, but it includes the two address bytes and the checksum as well. The address is 4 characters, but a 2-byte 16-bit address. And then the data will in fact normally be in blocks of, say, 16 bytes or 32 bytes quite often. And in general, the count value will not refer to the total number of data bytes. The total number of data bytes will be the count minus 3 and then multiply by 2 to get the number of characters. So we'll look at that in an example file in a minute. And then the checksum is a fairly simple checksum. It's just the sum of the count, the address, and all the data values. And then finally, that value is then complemented, so all the bits are reversed. And for no data, the count will still be 3, so it will be 0, 3 for the address and the checksum. So 2 bytes for the address and 1 for the checksum. And in fact, for the S9 record, and generally it only includes the count of 0, 3. The address for the moment we'll just be using as all zeros. It would be possible to extend the monitor to take that execution address and perhaps preload the go value for the monitor. But at the moment, the monitor doesn't save the previous go value used, so we can't really use it at the moment. And then finally, the checksum, because the checksum will just be the sum of the byte values, which is going to be 3, and the complement of that is FC. Now, one of the other interesting things is that Notepad++ also can validate SREC files and validate the checksum, and I'll just show you that. So if we go to a sample I've got here, and see here that we've got S1 all the way down to S9, and we can see there's a checksum there. And if we were to go in and change any byte values, so if I just change the first byte from 0 to 1, for example, I go to the next line, you can see that it's now telling me that the checksum is incorrect for that row. So if we change it back, we change one of the addresses as well, you'll get an invalid one. And if you change the checksum itself, again, it will show as invalid. So it's quite a useful thing. If you open this in Notepad++, we can check that it's okay. And in fact, in this particular one, we can see that the length here is 23 hexadecimal. So that means we've got the 3 bytes for the address and the checksum. And then the data here, if we just select the data and we see what the count is down the bottom, we can see here we've got 64 characters selected, which would equal 32 bytes. So that's 20 in hexadecimal. So with the address and the checksum, that gives us 23 in hexadecimal number of bytes. And then we can see at the end here, the last record does not have this number of bytes. Now, I think in the nanocomp code, I seem to remember we're going to be doing things in blocks of 16 rather than 32, but it doesn't really matter. It's valid either way. I think there is a maximum length for the SREC format, so there is a limit on how many bytes you can include on a line. What we're going to do now is to look at the source code that we disassembled back in video 12 with one. I've augmented a lot of extra comment and save. So we've got the documentation on load from serial port in version 2 of the monitor, and it says that when finished, the display will be F for finished, E for a hex error, or C for a checksum error. So when we look at the code, we'll see that we'll have the different exit conditions that will determine that character to be shown in the display. The next bit here is, this is the loop in the monitor command loop where we're waiting for a key to be pressed. So in fact, when the key L is pressed, this is what then goes off and calls the load routine. And in the load routine, it's very similar to what we've already done in the test programs from the serial port. We need to do the master reset for the serial port to let all the clocks synchronize. Then we are setting the control port to set the baud rate. So divide by 64 in this case will give us 9600 baud, 8 bits, no parity, 1 stop bit, and setting request to send below. And then what we then are doing is calling the receive byte routine. Now the receive byte routine is defined a little bit lower down here. And if we just set a label here, we'll just look for receive byte. There are quite a few instances of the receive byte. And what the receive byte does is it sets A to be the mask bit for the received data register full value. So there's a bit in the status register. It then tests the serial status port for that bit. When it's 1, it means it has data. When it's 0, it means there's no data there yet. So then what this does is then loops back and waits until we have some data. Once it has some data, loads the data register into A and then returns. So it's a very simple loop, but just makes use of the polling the status register. Obviously, if we used interrupts, then we wouldn't have to do that polling. We could just wait for the interrupt to occur, but we don't really need to do that for this monitor. It's much simpler to do it this way. So if we now go back to the point where we left that, so that's receive byte. So what we're doing is, first of all, we always expect the SREC format to include an S1 as the first record that we're going to be receiving. And so what this will do is just wait for an S to be entered. Once an S has been received, it will then look to see whether or not we've got a 1. If we've got a 1, then we start the loading process. If we got a 9, then that would mean that we got to the end. It may be possible just to send a record with just the S9 record in there. And that could be one of the tests we can try out later. Once it's coming to process the S9 record, what it then just does is stop. So it doesn't do anything with the S9 record at the moment. Obviously, if we wanted to load the address value into a default value for Go, then we might need to do something else here. And it will just show the F for finished. But under normal circumstances, the S1 record, we've got load 2 here. And what this is doing is using a common subroutine here, receive hex byte. So if we go and have a look at this, you can see it's used a number of places. But the receive hex byte saves the value which we've got in the A register. So A register is going to have the running total of the checksum generally. We then call a routine to receive byte value, and then we call a routine to convert that into hexadecimal value. So what it's going to do first of all is return the least significant nibble into a binary value, the first byte into the binary value, and then what this is then doing is logically shift left that, so the bottom 4 bits then become the top 4 bits, and then this is a typical trick that we do, then copy that into the B register, which is A off the stack. And this is a way of adding A to B, and you'll see this in quite a few places. So that receive hex byte is a way of receiving the full binary value. So the first byte that we receive is in fact the count of the number of bytes in the record. So what we do here first of all is we initialize the checksum in A with the byte count, because it's always going to start with the byte count, and then the value that we've got, the byte count, we just decrement, and we will then continue to receive bytes. So we'll first get the high address byte, and then we'll get the low address byte, and we'll store those in X. So what we've done here is we've checked to see if there's any more bytes. If there aren't any more, then we'll go to done. So we get the checksum from the last row in the SREC format. We complement it because it's actually a complement, and then we compare it. If they're equal, then we go back to restart the next row. If they're not, then what we do is to load A with the C value in the checksum, and then it will fall through here and basically just displays the error. Clears the display, displays the C in the next byte, and then just calls display refresh and just goes around in a continuous loop until we press reset. The load is a little bit simpler. The save is a bit more complex. So if you go back to the beginning and we look for save, we can see here this is the loop where when they press the save key. And then with save, what we need to do first of all is to display an S for the start address. We then get the address and store that in pointer. That's the start address. Then we prompt with F and get the finish address. We set up the serial port in the same way we've done previously. Then what we've got to do is to do some calculations on how we're going to send the chunks of data. This little section here is a little confusing. It effectively subtracts -1 from B, so it effectively adds 1 to B. And if you think about this, if we said we were only going to send memory from 1000 to, say, 100F, so F is a value of 15. However, there are 16 bytes because we've got the 0 value plus F. So we're always going to need to add 1 onto the address when we're doing the number of bytes that we need to do things on. Then we're doing some calculations here to say we're doing a maximum of 16 bytes at a time, 0 to F. And then what we then do is to start the checksum with a value of 4, because the length starts at 4. That means we've got 2 for the address, 1 for the checksum, and then to allow for our data 0 value, we're going to add 1 there. And then we send the length of that in hex to the computer, and then we store that in the checksum. Then we take the most significant byte of the start address and we send that to the computer in hexadecimal. We also add the binary value of the checksum to the checksum. So then we add 1 to the value of X to get the least significant byte of the start address, and we send that as hexadecimal, and then we do the same with the checksum. So when we come to send the data, we have this routine here, which we'll have a look at and see what that does. So send byte at X, what that does is effectively takes the value of X, finds the value of A at X, and then saves it a couple of times because we'll need to do it, use its return values and things. And then what we do is we mask out the most significant high nibble, a nibble being the 2 components of a hexadecimal digit. So the most significant nibble is the left-hand one, and the least significant nibble is the right-hand one. Having done that, we then logically shift right that value, so effectively move that high nibble value down to the low nibble value. And then this routine here is actually quite a clever way of converting the binary hexadecimal value into its corresponding hex character. Now, I won't go through the exact detail how this does it. It's referenced in Lance Leventhal's book, but effectively what it does is makes use of the decimal add adjust, which can do things, allows you to effectively use binary coded decimal values in hexadecimal. And what this makes use of is by adding 90, that effectively sets a carry for values from A to F. And then when we add 40 to it, it makes all the decimal values go into the 130 or the 141 range. The 141 has got the extra 1 in the carry because the values that you see for 0 to 9 are 30 to 39, but the values for A to F effectively have an extra 1 in there. So the A is a value 10, but effectively you need an extra 1 in there, and that's a value 5, and that you need an extra 1 in. So what this calculation here does is makes use of the decimal adjust and the add carry. So that really means that for values for the A to F, it has the extra 1 in there. So it's a very clever and efficient way of doing things. I think this is probably the most efficient way how to convert a binary value into an ASCII hex value. We send the value here to the serial port, then we get the saved input value that we've received, we mask out the low nibble this time, and we go through exactly the same value to hexadecimal character conversion and send it. This process continues, maintaining the checksum, and eventually once we get at the end of each block, we will get the checksum value, we complement it, which means invert all the bits. Then we send the value of the checksum as 2 hexed characters. We send a carriage return line feed to the end, and then we do a test to see has the value of X got to be equal to the finish address. If it is, then we go to send the end of file, and the end of file basically is just the S9 record. You'll see that in fact there's a routine send a message, and what it does is just uses the pointer to that message to just the ASCII values of S903, and that's all there is to it. So that's I mean, it's quite complicated, the code within the send and the load, but it was similar to the code that already existed. The only bits that needed to be changed in a major way is some of the checksum calculations and the fact that the original code would send 1s and 0s as 2 different frequencies by toggling a bit on the parallel interface adapter, whereas what we've just been able to do here is take the full value and send it to the serial port, which makes it a bit simpler. So what we're going to do now is to compile this, and we'll burn this into a new EPROM, and then we'll replace the EPROM and see whether or not this works. So I've got some commands here. So we're just going to copy this command. You'll see here we're using the -b value on here. If we use -s, then the assembler will in fact generate an SREC format. So let me just paste that in there. Okay, so I've got my EPROM programmer. I've got another Atmel AT28C64, so this is an 8 kilobyte EPROM. I've got the label for it, and what I've also got here is a zero insertion for socket. Now I've soldered some connectors onto there to make the pins a bit longer. The default pins on these are just a little bit too short to plug into a breadboard properly, but this means if we have to keep on reprogramming the chip as we make bug fixes and things like that, we don't end up bending all the pins and things, so it makes life a bit easier when we have to keep on updating things. So what I'm going to do now is to program this. We'll run up XGPro, which is the programmer. So just check, you see the pin 1 goes at the top there, pin 1 is there. And then if we go back to our desktop, so this is XGPro. You can see since I've used it last, an upgrade is available, so the software does get updated quite frequently here. You can see we've already got the Atmel 28C64B already loaded, so we don't really need to change that. The one thing we do still need to remember is about unprotecting before programming. So what we're going to do now is to load the file. So we need to go to the folder where I was doing this, in my breadboarding folder. It's the serial port. And we've got the V2 documentation version in binary. And we don't want to change where this is offset from. In later versions, we might choose to put some offsets in here to put it at the top of the ROM, but for the moment, we don't need to worry about that. I'll just check here, we've got 10 CE there, and the end we should have our reset vector, which is 7D89. So at around 7FF, we should have, there we go. So at 7FF, we've got 7D89, and the rest of this will just be set to the default of FF, which is what the ROMs tend to be. What we need to do now is to click on Program, and just need to make sure we uncheck the unprotect before programming. If we don't do that, it will fail. So now we're just going to hit Program. And that's it. So it seems to have programmed okay. So what I'm going to do now is to stick the label on it, and we'll plug it into the Nanocomp. Let's just take it out, and we'll stick the label on and then get in the Nanocomp. That's pretty reasonable. And what I will do is just put a V2 on here so we know it's the later version. Okay. Okay, so I've got the Nanocomp here, and you can see this is where the current ROM is down here. It's the Atmel 28C64B. And all we're going to do is to pull this out, and I have got a chip puller here. It's probably easier to use than putting a screwdriver in here. We just lift that out. Just need to be careful in that the pin 1 is not connected, so we just need to make sure that we take that into account when we plug this in and make sure those are. So this is our zero insertion force socket, and all I need to do is to make sure I plug this in along with the so I'm just checking that pin 1 does not have anything connected to it. These are the ones do. If we just check on the other side, make sure that's all correct. We probably just need to make sure we plug these ones back in. So yeah, those have become detached. So we just need to make sure we get the right addresses, otherwise it's all going to go horribly wrong. Right, so I've hooked up the power. I just put it over to the left-hand side here. We've hooked up the serial port to the PC, and I've actually run up the real-time terminal emulator. And all we're going to do now is to plug this in, see if we get the prompt. There we go. So we've got the dash there, and we can see it's about 4.91 volts. So that's good. So what I'm going to do first of all is to go into save an area of memory. So I think what we'll do 7800, and you can see here it's asking me for the finish address. So what I'll do is I'll do 78FF. Now I'm going to press the last F once where I switch to the screen. I'm now going to screen share, and hopefully you can now see real term. And what we'd expect to see here will be when we hit the F, we should see a number of rows, probably about 16 rows of S record format. There we go. So we can see here on our first row, so this is S1, we've got 1.3. So what we know that means is because there's 3 bytes, no data, that means we've got 16 bytes of data, so 1.3 in total. It starts at 7800. Now we've got 10 CE 1390, which is what we expect. And then we then have, we'd expect 16 lines, and then S90300, and then we should have checksum there. But the checksum doesn't look quite right for some reason. So what I'm going to do is to redo that again, but what I'm going to do now is to use the capture feature here, 7800 to 78FF, 78FF dot srec. Okay. Start overwrite, and we're just going to do this exactly again. So I'm just going to go in and do send 7800 78FF. And hopefully if we now stop the capture, we should be able to load that. Okay, so the issue we had was that we've got the invalid checksum at the end here. And if we go to the output file from the assembler, this is the end of file message. So this should be C on the end. Now I can see here we've got a label here, ASCII F, ASCII C, so it should be FC. And in fact, when we look at the bytes here, we've got 5643. Now, if we look at an ASCII table, and There happens to be one in Lance Leventhal's book. What we can see, in fact, if we look at V is 5/6 and F is 4/6. So it looks like we've got a 5/6 rather than a 4/6. So we probably just need to have a look. So if you have a look at the listing of our Nanocomp V2, we can see here the send end of file message is defined here, and we can see here the bytes, and we should have an ASCII F here. See ASCII F, but in fact the ASCII F, rather than being 4/6, is 5/6. So if we just find our definition of ASCII F, we can see in fact, yeah, this is 5/6, not 4/6. So this is a listing. We'll just go into the source and find this again, and we'll change this to 4/6, and then we'll recompile. If I just take a copy of the compile command here. So we've opened our command prompt, and all we're going to do now is to paste in the command line, and we'll run that. All we need to do now is to burn the updated image into the EPROM. We're just going to turn everything off. We're going to get our EPROM programmer here. This is where the advantage of the zero insertion force socket comes. We can just take that out to make sure we have it the right way around. And then we'll switch back to... Now all we need to do is to load the updated file. It's the same. And we should find that there will be a byte somewhere down the end here where it will be different. Not sure if we can see that easily, but somewhere down the bottom here there'll be a byte which is different. Anyway, we just program this. There we go, that's programmed. Just take it out. Take it out and we'll plug it back in. And we'll power things on again. See if that's come back up again. And so we'll go back to the, what we're going to do is to save 7800 78F, and we don't press the final F until we're back on the main screen. So if we get rid of XG Pro and we go back to our terminal emulator. Okay, so what we want to do here is to send this, and we should see that there is an FC on the end rather than a VC. So if I just type in F, and now we see in the end here, yeah, we now have got FC, so that should be okay. I'll do this again, and we're going to capture. We're just going to capture this file again, and hopefully it will overwrite it. We're going to start overwrite. So we're just going to do this one more time. So save 7800 to 78F, and then do start overwrite F. And that should have finished. It's finished, yep. Stop capture, and now if we go back to here, we should find now, yep. And in fact now we've now got the correct value. So there was a minor problem, but just shows that the zero insertion force sockets, we can make changes quite quickly. Now the only thing I would say is probably want to put the EPROM program the same orientation as where the chip goes, otherwise you may switch them around. Okay, so what we're going to do now is to test the load function on the Nanocomp. So what we're going to do first of all is just to take one of the sample programs we've had before. So we have here the serial out program that sends hello world. All I'm going to do is to take the -s version of this. What that will allow me to do is to generate an SREC format. We're just going to assemble that, and then we shall just have a quick look. We have the SREC file there. Open that in Notepad++. And we can see here that it starts at 1000 as the FC checksum and ends in 00. I think that should be, from memory, 103B or 3C, 103B. So that's what we're going to be receiving. And what I'm just going to show you now is the nanocomp, which I've already started up. Now if we look at the nanocomp here and we look at memory 1000, so you've got FF, D2, DC, 6A. There isn't anything executable there at the moment. What we're going to do is to press load on here and then just wait on the serial port, and I've plugged in the serial port for the USB over here, and I've also plugged in my KingStViz logic analyzer onto the receive and transmit pins as well, so we'll have a look at the serial communications on the logic analyzer in a minute as well. So we'll just press load. Now it's just sitting there waiting for the file to be sent. You just need to fire up the terminal emulator. We have Realterm running, and I'm just going to send the file serial out srec. That's sent, and if we look at the nanocomp display, we'll see once it's finished loading, we'll see there's an F there. And if we now go to memory 100, we see a 10CE 1200. So that's the first bit of the code. And if we go to memory 103B, I think it should be 00. So that's the end of the code. So loaded that correctly. So what we're going to do now is just to try and execute that. Go 1000, and we should then, if we go back to our screen, see we've got hello world. So that's the program running. What I'm just going to do now is to switch on the logic analyzer and repeat that, and we're just going to see what the logic analyzer shows for this. So we're going to look at the download first. So this means it's configured for receive. So the logic analyzer is set up here on the receive port. We have an analyzer which is an UART RS232. What this means is it will understand the baud rate and 8 bits, one stop bit, no parity. So as long as you have this stuff correct, it should be able to understand the serial communications. And as well, we have on the display format, it should be showing the ASCII and the hex. If we remember, the first part of this file should be S123 for the length, 10000 10CE112. If we look at that in hexadecimal, see that's 533132 starts from. That's what we expect. So what we're going to do now is to send the file again, and we will start this waiting for data. So it will be waiting for the trigger. And all we're going to do now is to put the nanocomp in load mode, send the file, and we can see it sampling. We can end the sample because we know we've got all the data there. If we just zoom into the data here, we can see that the serial data has been decoded, and we've got 53, which is S3132, so that's S123, which is the length, 1000, and 10CE120. So that's what we expect. That's working that way okay. So if we now just change it to look at the uploading data, and all I'm going to do here for uploading data is I'm going to save the same area of memory that we did last time, so 7800 to 78FF. Just wait to do the FF. We're now waiting for the output here, and then I'll just press F, and now that's finished. If you see here, we can now see the uploading 7FF data, and if you remember, we had this on the screen here. We would expect to see S113 7800 10CE1390 in this particular case. Let's have a quick look, and we've got 3131, so that's S1, 13 is the length, 7800, 10CE, 1390. So again, that all seems to be working correctly. So what this just shows is how we can use a logic analyzer to analyze serial communications, and you can use this for troubleshooting. And if we are having problems with the baud rate, frequency, or stop bits, things like that, we'd be able to drill into this and see what was actually going. So that's the end of video 15. So what we've shown in this video is we've updated the monitor ROM to do save and load using the SREC format, and we've solved a problem where we saw the checksum wasn't quite right. It was being uploaded from the NanoComp, so we fixed the code where that declaration of a ASCII F was incorrect. What we've then just shown you is testing the loading of data from the PC down onto NanoComp, so that'll be particularly useful because as we start to develop more complex software, it means we don't have to type in the bytes anymore. We can just load the assembled SREC output file from the assembler straight down into the NanoComp. And then we finally looked at the logic analyzer, showing how we can look at serial communications using the logic analyzer. So in the next video, what we'll be looking at is putting some buffer chips on the NanoComp. So where we've got all the jumper cables, we're going to be putting in an extra board there and putting some buffer chips between the processor and the rest of the board. This is because when we start to add more chips, then the ability of the processor to drive more than 4 inputs is restricted. So we need buffer chips in there to be capable of driving more TTL loads. And then we're also going to fix the power supply. So at the moment, the power is just chained together by the various boards. And what I'll show you is how I found the most reliable way to do power to these larger breadboard projects. So I hope you found it interesting. If you don't want to miss out on future videos, please hit subscribe. And if you can hit like as well, it just helps to push the videos further up the YouTube ranking so more people get to see them. Thanks for watching.